So our next speaker is Ted Jacobson, talking about space-time analogues and the Planckian puzzle. Please go ahead.
Okay, thank you very much. Thanks for organizing this meeting, which is a great place for me to learn about amazing things that experimentalists are doing, and also about the theory that I have always wanted to know about. I feel a little bit, I have to apologize that my talk won't integrate very well with the rest of the talks, I think. But on reflection, I decided I just wanted to speak about the issue that really drove me to be interested in the first place in analogues of condensed matter and fundamental physics. With the hope that actually with all the expertise, both experimental and theoretical, people I don't know at the meeting, somehow I could, it's a selfish motivation, I could get new inputs and maybe some people would be interested and see ways to make headway that I'd never thought about. So I'm just going to go back to the beginning. It started for me in the late 1980s, actually, when I got fed up with trying to think directly about quantum gravity. And I focused on this strange puzzle that comes up in the Hawking effect, which I think it was Gerard 't Hooft referred to as the Planckian regime or problem or something like that. I'm not sure what the last word of his was. Here's a picture of the problem. Well, I'll introduce it. Here's a picture of by Roger Penrose of space-time with collapsing matter that makes a black hole. And the black hole emits Hawking radiation. The temperature is h bar times the surface gravity kappa divided by 2 pi. The surface gravity for a spherical black hole is just like the speed of light divided by twice the horizon radius. So it's sort of the light crossing time, inverse light crossing time of the black hole. It's different for a rotating black hole, but we don't need to get into that. The numerical value is 62 nanokelvin if the black hole has a mass of the sun, and it's inversely proportional to the mass for a spherical black hole. So what is the Hawking radiation and why does it happen? The key thing to me is this picture, where you think about once the black hole is formed, it's just sitting there classically. It's a stationary space-time geometry. And the symmetry associated with that stationarity is time translation, at least outside the horizon. It's a time translation. I've drawn on this picture, the red arrows are the time translation vector that moves the space-time forward. Once the collapse is finished, nothing else is changing. But the issue is that that symmetry is actually not a time translation inside the horizon. If you, just by looking at the picture, you see that at the horizon, it's moving along the edge of the light cone. So it's a light-like translation, and inside it's space-like. So although there's a conserved quantity because you have a symmetry, that quantity locally inside the horizon would be identified as a momentum, not as an energy, because it's a space translation, not a time translation. And since momentum is not bounded below for, a physically stable system, there's no ground state. I mean, you can create negative conserved quantity excitations inside the horizon, and they can balance positive conserved quantity excitations outside, and thus there's an instability of the vacuum. And that instability basically is the Hawking effect. So it leads to a kind of pair production, or I like to think of it as a tidal peeling off of vacuum fluctuations. Just outside the horizon, an outgoing propagating mode can just barely escape, maybe after hovering for a while outside the horizon. And just inside, it's inevitable that that field mode would finally fall into the singularity in the middle. So the vacuum is sort of peeled apart by the gravitational tidal effect. And that peeling corresponds to exciting modes that would otherwise have been in their vacuum state. And the excitation is thermal. In fact, the full state looks like what I've written here. It's an entangled, for each mode, this is a simple description for a free field. For each mode, it has an excitation number n, it's like a harmonic oscillator, and that's indeterminate, but whatever it is for the outside particle, its partner mode on the inside is correlated to it, and the amplitude for that excitation is this exponential minus the energy of the mode divided by twice the Hawking temperature. So that if you have only access to the outside and therefore trace over all the interior degrees of freedom, this becomes a thermal density matrix for the exterior modes at the Hawking temperature. Now here's the Planckian problem. So what's wrong with this? This is great, it's been derived in many ways, but if we look at it a little more, this is something that actually was first pointed out to me the first time I ever learned about the Hawking effect. Bill Unruh was visiting University of Texas, where I was a graduate student. He explained the Hawking effect to me and explained this puzzle. So it sort of stuck with me for the rest of my life, and it probably will to my grave. So here's the problem. Here's maybe I can find a pen here too. Hold on a sec. Like 2 points somehow. Okay, so here we're looking, can you see that? Yeah, I should make it a little bit darker. I'll do it in red. At an outgoing Hawking quantum that's managed to emerge from the black hole in some, some mixture of excited states. And we're gonna trace it back to the black hole where it came from. This is a mode of a field. So it propagates, let's say it's a massless field, it propagates at the speed of light up here. We trace it back to the horizon where it's getting blue shifted and closer to the horizon. And the frequency of that mode, when I observe it out here, is the Hawking frequency, let's say, if it's a typical excitation in the Hawking flux. But that frequency would be measured quite differently by a freely falling observer that falls into the black hole here. And the difference grows as the time interval here between, let's say, the infall and the observation grows. And the relative redshift grows exponentially with the surface gravity, according to this formula here. So it's an exponential growth of frequency omega naught, which is the ingoing free fall measurement relative to the outgoing Hawking frequency. Now, as you know, exponentials are big. If we take a solar mass black hole, after 2 seconds, this exponential is grown to the power e to the 100,000 power. Okay, so we're talking about not just a Planckian field mode, we're talking about something that's absurdly beyond the range of any physics that has ever been probed, and probably is meaningless and doesn't exist in nature. It's also problematic theoretically, because if that mode did exist in nature, we would have this Planckian reservoir of modes outside the horizon that would all contribute to black hole entropy, and we would have an entropy much greater than the Bekenstein-Hawking entropy. So it must be possible to understand the physics of the Hawking effect and of the outgoing modes without these Planckian modes. So it is possible. So let me first just describe, if you want to just avoid the problem and give yourself confidence that the Hawking effect actually occurs despite this apparent need for these Planckian modes, you can just focus on a patch of the horizon that I've drawn in that blue oval. And instead of tracing the Hawking particles back so far that its ancestor frequency becomes Planckian, just trace it back until it's got a very high frequency compared to the light crossing time of the black hole, but still very short very small compared to the Planck frequency. So this could be like, if it's a solar mass black hole, it's a 3-kilometer radius, take it till its wavelength, trace it back till its wavelength is 1 centimeter or something like that, or even, micron. It doesn't have to be anything even subatomic. As long as the quantum state of the field in that little blue oval, as measured by local probes falling across the horizon, is the local ground state, not at Planckian frequencies, but just at these, centimeter wavelengths, then the Hawking derivation applies, and we can infer that we get the Hawking effect. So it's a kind of a low energy effective derivation of the Hawking effect is perfectly possible. provided the input is that the field at the horizon in the blue oval at that intermediate length scale is the local ground state. So that's a very natural assumption that it would be, because for millimeter wavelength excitations and a macroscopic kilometer-sized black hole, there's no reason to think that those modes would be excited. So it's a natural assumption, but it's not something we can derive within the theory that we understand, because if we try to derive it, that means we want to put in an initial condition and evolve the initial condition and show that this ground state condition holds. But we can't do that, because if we try to trace back to an earlier time, we hit the Planckian problem. So the puzzle for me isn't so much whether the Hawking effect occurs, because this and other arguments make it extremely plausible that it does. The deep puzzle for me that I can't let go of is, where do the outgoing modes come from? If they don't come from a Planckian reservoir, they have to come from somewhere else. They have to sort of reconstitute. And that's fine to say, but it seems to violate Lorentz symmetry, local Lorentz symmetry. Because any freely falling observer crossing the horizon in a small region can't tell they're in a black hole space-time. They just see a local, almost flat space-time. So to impose some kind of a cutoff on the field modes at that place for that observer violates local Lorentz symmetry. So if such a thing exists, such a cutoff exists, it has to somehow mix global features of the black hole space-time and the local processes near the horizon. And it's not understood at all how that happens. So I'm really speaking here about something I don't understand at all. But I will start, though, by talking about things I do understand, which is condensed matter analogues, in which this question is resolved in a completely concrete way that's easy to understand. That's nice, and it may provide guidance, but it doesn't seem to be the way that it could work in space-time because of the local Lorentz violation. So let me now go to this condensed matter analog, where we do understand the resolution of this puzzle. Bill Unruh, as I just mentioned, told me about this, and this got him also thinking about how to understand it better. And I think that's the main reason he introduced the idea in 1980 of the sonic analog black hole, because so he considered the fact that a fluid flowing faster than the speed of sound, or an inhomogeneous velocity flow that could exceed the speed of sound somewhere, would in effect create a horizon for sound. And by thinking about the derivation of the Hawking effect, he argued that if that fluid were a quantum fluid, in fact, the horizon would emit sonic Hawking radiation, phonons, at a temperature determined just like Hawking's by a surface gravity, but in this case, the surface gravity is defined here as I have written the gradient of the velocity evaluated at the horizon. This is assuming the speed of sound is constant everywhere in the fluid. If it's not constant, then we have to add the speed of sound to the velocity of the flow and take the gradient of that. So he made that prediction, a long 40 years ago. Recently, it's actually been confirmed by Jeff Steinhauer using a Bose-Einstein condensate for the fluid. And that's not the only realization of this concept one could have, but let me start, I think, with that one. When actually I first wanted to mention, the analogy is extremely close in the sense that you can even construct a space-time metric out of the fluid parameters, such that the sound waves propagate in this curved space-time as, in the fluid as they would in this curved space-time. The metric has, this is the velocity of the flow, the density of the fluid, and the speed of sound in the fluid. But the details here are not important for the conceptual part I want to focus on. So given this idea of sonic black holes, we can hope to study the things I just mentioned. The Planckian problem should have some resolution because a fluid has a molecular short distance cutoff, and yet it produces this radiation. we can understand how it is that the outgoing vacuum is delivered as an adiabatic process from the initial state. And also this quantum entanglement of the Hawking quanta and their partners even can be studied in a laboratory, because unlike a real black hole, in a laboratory, you could reach behind the sonic horizon with one. Maybe I'll just move on here. I'm contrasting the different ways that the trans-Planckian puzzle can be resolved in a condensed matter system or possibly in nature. So we're looking here at a diagram in space-time of a Hawking quantum and its partner behind the horizon. In the usual relativistic picture, the blue shifting backwards in time here is without bound. If in a Bose-Einstein condensate, the dispersion relation becomes superluminal at large enough wave number. So what happens is once a certain amount of blue shifting has happened, the propagation becomes superluminal and the particle and partner have actually emerged from behind the horizon. So this is how there's a cutoff on this trans-Planckian regime. There could also be a subluminal dispersion relation, and that's the one I'm actually going to focus on in most of the talk. And then there could be something which is even more interesting and probably more physically correct, where really the modes simply don't exist at all before once they reach some scale. They just kind of mix into a soup from which they emerge when you go forwards in time. And it's the understanding of how this emergence happens that I'm after. Something like that has to happen in space-time, and yet to be consistent with Lorentz symmetry and diffeomorphism symmetry. So here's the way it works for a Bose-Einstein condensate. We have a speed of sound, a low frequency speed of sound or low wave vector speed of sound at a sufficiently high wave vector. We get a quartic term in this dispersion relation. This is just corresponds to a single particle dispersion relation. So the phonon, which is a collective mode, kind of starts to resolve into a single particle excitation, which is like superluminal, supersonic. And so the dispersion relation curves up, and therefore we get that picture that I described, that I just showed earlier for where the outgoing Hawking quanta come from. The first dispersion relation I thought about many years ago when I started thinking about this, that was before Bose-Einstein condensates had been realized in the laboratory. So I thought about the only quantum fluid I knew about at the time, which was superfluid helium-4. And in that case, the dispersion is subsonic as the wave number starts growing. And that means that a wave packet traced backwards towards the horizon, instead of speeding up and crossing it like that, will actually come to a turning point and then recede from the horizon. And then because of the complication of this oscillation in the helium dispersion relation, it would actually kind of wiggle around if you trace the motion of a wave packet, assuming it propagates like a particle whose Hamiltonian is determined by this dispersion relation. It'll just track along here until it reaches the end where it becomes unstable and kind of decay into rotons. So the picture physically would be that somehow out of this, the short distance degrees of freedom of this jostling superfluid helium-4, the modes kind of assemble themselves and emerge from the horizon like that, eventually to come out thermally populated. So this is a very complicated system. I couldn't really understand a many-body system. And so this led to this whole enterprise of which Bill introduced, of using a free field theory with a artificially imposed dispersion relations. And one of the instantiations of that I want to focus on for here, because it connects to the issue of, I think it does, to anomalies and the Robinson-Wilczek paper that was mentioned by Karl Landsteiner earlier, is a lattice model.
Hi. Sorry, can I? I'm Karl, by the way. Can I ask a question to the previous slide?
Yeah.
Yeah. Is this an instance of this Landau criterion for the instability of a superflow?
No, I don't think so.
Different.
In fact, that the Landau, that would be if you tried to realize this experimentally, I think the Landau instability would be an obstacle.
Okay.
Probably. Okay, so what I'd like to tell you about is this lattice model that I developed with my student David Mattingly about 20 years ago. This is, to me, a really beautiful model that shows how the Hawking process could happen on a lattice. The lattice we're considering is drawn in the picture. It's falling into the black hole. So time is a vertical axis, space is horizontal, and the initial time here is 0. The lattice is equally spaced here outside the horizon. The lattice points are equally spaced. And then they fall freely into the black hole. The reason we want them to fall freely is if you try to make a time translation invariant lattice where you just take one of these lattice point trajectories and then translate it discretely in time by a fixed amount, you could create a lattice with discrete time translation symmetry. The problem with that is that the lattice spacing would would converge to 0 at infinity. And that wouldn't really be a regulation, and it would actually play a crucial role, that short distance lattice spacing, in the Hawking effect. So we also considered that with a previous student, Steve Corley, but this model is more adapted to the physical idea that there's some short distance cutoff, like in the superfluid helium or in nature maybe, which just simply doesn't support transplanckian modes. The drawback of this lattice is that the lattice spacing at the horizon is growing in time, as you can even just see on the picture. Because things, the closer they are to the horizon, the faster they start falling in, these lattice points. All right, so that's the lattice we set up. Let me maybe summarize the finding by reading you this abstract, because it's brief and to the point. So we consider a scalar field theory on this lattice. It's 1 + 1 dimensional. The outgoing modes arise from incoming modes by a process that's basically a block oscillation, a single block oscillation on the lattice, as I'll explain in the next slide, I think with a dispersion relation. So in other words, if we take, say, this outgoing positive frequency mode here and propagate it backwards in time on the lattice, it reaches the point where its frequency is high enough and its wavelength is short enough to feel the lattice structure, and it turns around. And then it's also eventually short enough to feel the time dependence of the lattice. So its frequency then, it doesn't have a conserved killing frequency anymore, and it propagates out. For a while, it's affected by that time dependence. Then it's back into the asymptotic region. I'm going backwards in time now. And here it's a superposition of a positive frequency component and a negative frequency component, even though up here it was purely positive frequency. And the Hawking effect is the fact that there's some negative frequency component. And by computing the amplitude of that, we're able to calculate what's the flux. If the state coming in was the ground state for all modes, then the state coming out would be an excited state that's thermally excited. And we confirmed that by numerical evolution on this lattice. Let me tell you a little bit more about it so you can see why that would happen. So it's like taking a metric of a black hole, but expressing it in unusual coordinates that are like Gaussian normal coordinates. Z is constant on a lattice point world line, so we're going to discretize the Z coordinate. And then T is the proper time along the world lines of the lattice points. And if we plug that into the action for a massless scalar field and discretize the Z coordinate, we get this action that I've written here, where A of T is this, the value of this time-dependent scale factor at the location of each lattice point. So that's the model. Now the dispersion relation, if you just look at one moment in time, and let's say where the scale factor is set equal to 1.
Ted, if I may interrupt, you've been speaking now for approximately 25 minutes. Just
okay, thank you. It's the usual lattice dispersion relation, and we can see on this graph how it is that this strange behavior of a mode that kind of reflects off the horizon works. So I'm going to start on the dispersion relation with a point that corresponds to a wave packet with a wave vector for an outgoing mode up here. That would correspond to something like this. And then if I trace that back to the horizon in the WKB approximation, it should ride along this dispersion curve. And it'll go up until it actually goes over the top and comes down the other side where it's now a left moving wave packet. This doesn't catch the fact that there's also a negative frequency component that's introduced because of non-adiabaticity near the horizon. But it does explain why it is that the wave packet reverses. So then it finally escapes to infinity, and so something like this evolves forwards in time like that along the dispersion curve. So it's quite similar to a Bloch oscillation sort of induced by the gravitational field of the associated with the black hole. Here's a numerical simulation, for example, of what it looks like for an actual wave packet running backwards in time. So here's the final wave packet. It's moving to the horizon is on the left. It's moving closer to the horizon. It can't cross the horizon because it can't go superluminal. So it just kind of gets stuck there. And as it sits near the horizon stuck, it starts to develop these very high oscillation wiggles. And eventually those assemble into a wave packet that propagates backwards away from the horizon. And then if we Fourier analyze this into its positive and negative frequency components, we find that it has both. And the amplitude of the negative frequency component tells us what the occupation number of the outgoing mode would be if the incoming state were the vacuum. I think since I'm almost out of time, I want to jump to the last part, some questions and the possible relation of this to the Robinson-Wilczek paper. So here's some questions about this model. The lattice dilutes, which is not satisfactory from a fundamental viewpoint. So could we make a higher dimensional model with a Hamiltonian lattice that doesn't have a diluting lattice? Like, for example, a molecular fluid would do that. But the problem is this lattice, although it's time dependent, it's slowly time dependent. And a fluid with atoms moving around at the atomic scale would seem to violate that slow adiabatic evolution at exactly the scale where we need it to be slow. But maybe if it's a quantum fluid, that would work. So that's one set of questions I have. Can this be redone without a dilution of the lattice? The lattice breaks local Lorentz symmetry, diff symmetry, and scale symmetry. And we don't expect those to be broken, at least at first, in quantum gravity. But maybe, and this is the question, could a quantum black hole spontaneously break one of these symmetries somehow because of kind of a UV-IR interaction between its global structure and its microscopic structure? We have a similar problem, by the way, in an expanding universe where there's a dilution of a lattice if you start with a fixed lattice spacing. Somehow a new idea is needed there. But let me end then on this question about this Robinson-Wilczek paper. For years, I've wanted to understand this, and I find it completely obscure. And since Carl mentioned it in his talk, I thought maybe he could help me understand it, he and or others. So let me just briefly tell you what I don't understand about this, or what they're saying and why I don't understand it. So they wrote this paper in 2005. They say that in order to avoid a breakdown of general covariance at the quantum level, the total flux in each outgoing partial wave must be equal to that of the black body spectrum. So there would be an anomaly, they're saying, a gravitational anomaly, if it weren't for having the Hawking effect. That's the basic claim. In this first paper, they have this beautiful picture which it's hard to understand. They say they're eliminating the outgoing modes inside this region very close to the horizon, because that gives them a chiral theory, because they have only they have only left moving modes. There's some gravitational anomaly, and that has to be canceled by Hawking flux across the horizon. The next year, Frank wrote a paper with some other authors, including charged black holes, and the story seemed to change because now they're neglecting the ingoing modes. So I don't understand either one, but the story changed without any explanation. And another aspect of the story changed. In the first paper, they used what's called the consistent anomaly to derive the Hawking flux. And in this paper, they used the covariant anomaly to derive the Hawking flux. Let me explain the key step in this paper, and that'll be basically the end. So one can derive a relationship using the covariant anomaly between the outgoing flux of energy at infinity, the surface gravity of the black hole. This would be exactly the Hawking flux in 1+1 dimensions, and a term on the horizon. And if this term on the horizon vanishes, then they've derived the Hawking flux. This term on the horizon represents the killing energy flux across the horizon. Now, what I understand is that doesn't vanish. There's a negative killing energy flux across the horizon that balances the positive killing energy flux to infinity. And that's why the Hawking process is consistent with conservation of the quantity conjugate to this symmetry of the black hole. But they want to say that, no, this quantity should vanish, at least in this theory where the ingoing modes are neglected. Well, the problem is, why should we neglect the ingoing modes, first of all? And second of all, this flux doesn't come from the ingoing modes, it comes from the outgoing modes. So I'm afraid that neither of these two papers makes any sense to me. And I'll end with this set of questions about them. Are either of them imposing the right boundary condition? Why should the energy momentum tensor vanish at the horizon? As I just said, there should be a negative energy flux across the horizon. And is the reason that these papers are giving for excluding the outgoing or maybe ingoing near horizon modes poorly conceived? If you read the paper by Robinson and Wilczek, in the preamble, they say these modes are somehow problematic because if you took the wrong vacuum state, namely the Bulwer vacuum, they would lead to an infinite energy density at the horizon. Okay, but you don't take the wrong vacuum. In the unroot vacuum state, it's a perfectly regular state. So I would like to propose, or I think that there's something right about this, and I don't know yet what it is, but my hunch is the following. The real reason why we should be thinking about excluding these modes is not because they're problematic, but because physically they're not there. For the reason I just explained on the lattice and in all of these condensed matter analogs. They simply don't exist. So what we really should be trying to do is figure out what it means to say we have an effective field theory which below some scale has outgoing modes, but in which those modes cannot be traced to trans-Planckian ancestors because those ancestors don't exist. So I feel there's something tantalizing about this Robinson-Wilczek idea, but as it stands, it makes no sense to me. And I'll end with that.
Thank you very much for this, I guess, provocative talk as we asked of the speakers. I think I saw one hand, and then it disappeared and it turned into a clapping hand. So are there questions for Ted, or perhaps answers, even better, I guess, from your
oh, that would be wonderful.
From your point of view,
or even just a partial answer. Does anybody think they understand the Robinson-Wilczek paper?
I guess Carl maybe wants to answer that question.
And the
I think-
answer is no.
Okay, that's a clear answer.
You know, if this is the one place, for example, where if we were at a workshop in person together, I feel like sitting, by a blackboard and talking about this would be great.
Yeah, I
So
think
I-
now it amounts to doing it via Slack, which is no substitute, clearly. I think Renee has maybe an answer or a question.
No, I don't have any answers about this particular paper either. But when you were talking about it, something came to my mind. So if this is effectively 1 + 1 dimensional calculation, it's well known from 2-dimensional conformal field theories in flat space that if you don't have the same number of left and right moving, or I guess in your case, in and outgoing modes, then you will have diffeomorphism anomaly, this disgravitational anomaly. So this is just wanted to say this. So I guess that's not under question. But as you say, the question is like, how do you get rid of the other trans-Planckian modes, basically, right?
Well, yes. I mean, I would have thought that would be what Robinson and Wilczek would have said, but that's not the reason they gave. But that's okay. I don't mind taking their framework and supplying a different reason for doing it. But I don't understand the framework either. Like their calculation and the basis for what they're doing, I can't follow. The end of the paper, by the way, the second paper that Frank wrote with Iso and Umetsu, they say, we assumed the covariant forms of energy momentum tensors should vanish at the horizon. They say that's natural because the physical conditions should be diffeomorphism invariant. But the previous paper, the one with Robinson and Wilczek, used the consistent anomaly and a different method of deriving the result. So at least I feel like we should be able to make progress understanding when should you use a consistent anomaly equation and when should you use a covariant anomaly equation? I don't know, even that I can't understand. So should you ever use a non-covariant equation? I mean, why does anybody ever talk about a consistent anomaly? I don't understand that.
Yeah, but maybe Carl can explain this better. But so
yeah,
the
this is something I can explain.
Okay, please go ahead.
So the actual consistent anomaly is the one that you can couple to a dynamical gauge field. Right. So for example, if you want to, just in QED, for example, and you want to have an electric current, which you can couple to a Maxwell field, then that current has to have the consistent anomaly, simply for the reason that you can adjust your regularization scheme in such a way that this consistent anomaly vanishes in the electric current. So, I mean, it's sort of a complicated story, but in this case, at least, this is a mixed anomaly, and actually, there's a whole one-parameter class of consistent anomalies, and there's one particular one where all the anomalies just in the axial current, and you have a conserved electric vector current, and that you can compute, that you can couple consistently to a gauge field. Now, in this case, when you have I think this is 1 + 1 dimensional, so you have a pure gravitational anomaly. In that case, sometimes it's just to my understanding, it's sometimes just a way of bookkeeping. So you decide what you keep on the right-hand side and you call it anomaly, and what you put on the left-hand side and call it contribution to the current. Right? Because every anomaly by itself is a total divergence. So, and typically you say the divergence of a conserved current doesn't vanish, but the anomaly itself is a total divergence. And then you can take part of this and put it to the other side and define specific criteria on this current. For example, you want that this current is by itself a gauge invariant object, even if the gauge symmetry is anomalous. But you can still define a gauge invariant current. And that would be the covariant current that fulfills the covariant anomaly. In some sense, that is in a way such just some bookkeeping, but here it's more, because here in this Robinson-Wilczek paper, it's really singled, this covariant current is singled out because it's the one that has to vanish on the horizon in order to get this derivation. But I don't have, in this particular context, I don't have much more insight into this. So another thing I can say is that typically when you apply this, say, to things like in this Weil semi-metals and so on, what the covariant anomaly catches is really just counting modes around the Fermi surface, say, for the fermionic system. That's easy to identify. But then there are contributions to this conserved numbers which come from the whole band topology. And this thing is captured by the consistent form of the anomaly. So at least in this particular instance, I think you understand what's the difference. Here in this gravitational, I'm not, I wouldn't go that far. But okay, I think that's as much as I can say now.
I think there's a very, I don't know, maybe condensed matter way of saying what Carl just said, which is you take a parabolic band and then imagine moving it up, just upwards, but focusing on the Fermi surface. Then, you know, if you just focus on the Fermi surface, it looks like you're creating particles out of nowhere. But in reality, you're not doing that. You're actually moving it up. Just all field states are moving up. And so this, if you just think about conserved currents, this ends up being the difference between consistent and covariant. Like just basically focusing at just the Fermi surface and seeing field states going up because you don't see the vacuum. You don't see that's a field band. Or simply, like if you just zoom out, you're just seeing a band going up, but there are no states appearing out of nowhere. So that's the two type of, let's say, conservation equations that you can write for those two situations are the consistent and covariant.
Sorry, which are the two? Which is which? That sounds interesting and it sounds relevant.
So the covariant anomaly would be the one where you just focus on the Fermi surface and you think that there's, you know, particles created out of nowhere.
Okay.
And the consistent one would be the one where you don't, the one where you actually conserve current. And this you can actually see, you know, in a lattice model quite simply. Like if you think of Weil semi, I don't know about in this context again, as Carl said, but in the context of Weil semi-metals, we know in a lattice, you know, we have a lattice model for Weil semi-metal, and then we can, you know, stretch it out and see how these effective gauge fields appear. And for those, you have a consistent version of the anomaly and covariant version of the anomaly. And so you can try to think, okay, from the lattice perspective, I can calculate every observable I want. So then I should be able to know which part corresponds to the consistent anomaly and which part contributes to the covariant part. And as Carl said, what you end up finding is that if you just look at the Fermi surface, you basically get the covariant version of the anomaly. While if you look at the contribution from all field states, like for example, a whole current would be like this. It would come from all field states. Then you would get the consistent version of the anomaly.
Mm-hmm. Thank you.
There's a question by Jaco.
Yeah, so let me try to, well, basically, I'm asking also a question. So one simple way how you could kind of mix the two is that you basically go back into this picture by Callan and Harvey, where basically you consider a domain wall. And now the difference between the covariant and consistent is basically depends on whether you are focusing on the fermions or on the theory which is living on the domain wall. And then you have the higher dimensional bulk theory, which is basically doing the consistent one. So in these gravitational anomaly papers, I already forgot, but I mean, if they're focusing on the mode, which is basically skimming the black hole, that would be 1 + 1d. But then, of course, if you want to get away from the black hole, you basically need an extra dimension. So that would basically give an easy explanation why you basically would have covariant anomaly on this 1+1D horizon, and then on this total space, where you can actually also leak away from the black hole, you would have the consistent one. So if the two papers basically first talk about the 1+1D horizon fermions, and then if on the next paper they talk about the kind of total space where you can also go away from this skimming orbit, then that would be one explanation. But I already forgot how it goes in the papers. And my confusion was always that in the first paper they speak about currents, and in the second paper they speak about energy momentum tensor. So then basically you started your talk with this kind of observation that once you cross the horizon, basically time and space interchange. So then I'm not sure whether that was only for motivation, but with regards to kind of the anomaly, that would perhaps be even, I don't know whether it makes it even kind of more confusing, but yeah, depends whether it was just kind of motivation or something kind of, yeah. So let me end it at that.
Mm-hmm. You know, each of these papers has over 300 citations, and I figured maybe people coming afterwards, you know, thought about it and cleared some of this up. But as far as I can see, every one of those papers just does mathematical manipulations and doesn't talk about the physical justification of anything.
Yeah, so let me comment that I think it's actually quite well known in the quantum Hall literature that this kind of covariant and consistent switch happens whether you consider just the boundary or the whole bulk with the consistent one. And as far as I remember, Mike Stone has at least one paper where he basically does the gravitational anomaly in the quantum Hall setup, where he considers the fermions on the boundary and then looks how the kind of, I guess he considers how the energy momentum leaks from this boundary to the bulk system. And that would be one example where you would expect that the anomaly basically goes from the covariant one to the consistent one.
Oh, that sounds helpful.
Yeah. Well, I can post the paper into the Slack or something like that, but
Great.
I think indeed such a paper exists.
Thank you.